Hey calculus, we are going to learn about derivatives. Believe it or not, you guys have been working with derivatives since algebra. All right, a derivative is a rate of change. And what else is a rate of change from algebra? The slope. All right, the derivative is the same as the slope of a function. Okay, when you find the rate of change between 2 points, using the slope formula, which is right here, the good old slope formula, y minus y over x minus x, that is called an average rate of change in the calculus world. So that slope formula, the slope between 2 points, is an average rate of change. If you want to find the derivative at a point, a specific x value, just one x value at an instant, that is the instantaneous rate of change, and that is the true definition of derivative. The derivative of a function is the rate of change of that function at any given instant, instantaneous rate of change. Okay, so I would strongly encourage you to read through this again. Graphically, on a graph, how can we find the derivative? In order to find the derivative, we need a slope. In order to find the slope, we need a line. So we use a tangent line. We draw in a tangent line. And as an example right here, this tangent line, the blue dotted line, is a tangent line. A tangent line is a line that hits a curve in one place. So we can draw in a tangent line at any specific x value, and we can find the slope of that tangent line, and thus we have the derivative at that point. Okay, the slope of the tangent line to the graph of a function called the derivative is given by this big messy formula right here. Okay, the first thing we need to understand is the notation for derivative. Up at the top of the page here, f of x, that is the notation for the original function. Okay, and that's what you're used to. You know that. F of x is the same as y is equal to. But now the notation for the derivative function is f prime of x. There's a little dash up in the upper right corner. F prime of x. That is the notation for the derivative function. All right, every function has its own derivative function, and it is called f prime of x. All right, it is read f prime of x, and I put that right down here for you, f prime of x. All right, so to find f prime of x, we use this big messy formula in the box. All right, it's in the box here for you. So let's look at it. You have a limit. A derivative is a limit. And then you have a big messy numerator. There's two parts of your numerator. The first part of your numerator is right here, f of x plus h. That just simply tells you to rewrite the function, all right, and you plug in x plus h for x. Everywhere you see x, you put in x plus h. So that's the first part of your numerator. The second part of your numerator right here is just the function. We just plug in the function as is, f of x. And the big important thing is you put that in parentheses. All right, that has to be in parentheses. Right here, parentheses, because you have to distribute that negative. All right, so we're going to practice that. Before we practice that, we just have to review function notation. So right up here, function notation. We have a function, f of x is 2x squared plus 3. What does f of 3 mean? That means we plug in 3 everywhere we see x. So it looks like this. We have 2 blank set of parentheses squared plus 3. And instead of x, we put in 3. All right, now we just go to work. The 2 comes down because we do exponents first. 3 squared, of course, gives me 9 plus 3. 2 times 9 gives me 18. 18 plus 3 is 21. So f of 3 is equal to 21. All right. Okay, now let's do f of negative 2. I like to write the function and put in a blank set of parentheses for x, 2x squared plus 3. Now, instead of x, I plug in negative 2. And then I just go to work. 2 comes down. Negative 2 squared is positive 4. Bring down the plus 3. 2 times 4 is 8. 8 plus 3 is equal to 11. All right, let's do the next one. F of h. Now we're plugging in h everywhere we see x. So we write the function, blank set of parentheses everywhere we see x. But now we just plug in h for x. And there's really nothing to simplify there. 2x squared plus, or 2h squared plus 3. Okay, and then finally, now we've got a trickier one. f of x plus h. We do the same thing. We write the function and we put in a blank set of parentheses everywhere we see x. But now we're plugging in x plus h. All right? So now we go to work. The 2 comes down. Remember, when we square something, we multiply it by itself. So we have to take x plus h and we have to multiply it by x plus h. All right? So that's what we just did. And then don't forget about the plus 3. Now, I'm going to bring the 2 down and I'm going to multiply these 2 together. You can either use FOIL or you can use area boxes. But if I square the first 2 terms, x times x gives me x squared. If I multiply the outside 2 terms, I get h times x times h. All right, I like to put them in alphabetical order. It really doesn't matter. So hx. All right, if I do the inside 2 terms, I have another h times x. So another plus hx. And finally, if I do the last 2 terms, h times h, that gives me h squared. All right, so when I square x plus h, I get this. Don't forget the plus 3 on the end. Now, let's look for like terms. Right here, we have 2 hx's. So that looks like this. X squared plus 2hx plus h squared plus 3. All right, so this one you're going to want to know. Whenever you square x plus h, you get 8x squared plus 2hx plus h squared. All right, now we distribute the 2x squared to each term, 4hx, 2h squared plus 3. And I don't see any like terms, so that is as far as we can go. But that's a pretty important problem. You're going to want to know how to square x plus h. Okay, let's use the definition to find the equation of the derivative function. The first thing we do is we set up the definition. So we have the limit as h approaches 0. The first part of the numerator, we rewrite the function, 5x plus 2. I like to put in a blank set of parentheses, and we plug in, everywhere we see x, we plug in x plus h. So that is the first part of our numerator right here. Sometimes it helps to diagram it. That is my f of x plus h. All right, the second part of my numerator, I make sure I put it in parentheses, and I just put in the function as is, 5x plus 2. So this is the second part of my numerator. That's my function. Make sure it's in parentheses. The denominator is just h. Now we go to work. The second step is just algebra. We expand that numerator. We have to distribute this 5. So we get 5x and then plus 5h. You work from left to right. Now we have plus 2, so that comes down, plus 2. And here, moving to the right, we have to distribute that negative. We get negative 5x, and then we get negative 2. Don't forget to distribute that negative. All over h. Okay, now if you do it correctly, a lot of things should cancel out. Look at this. We've got a positive 5x and a negative 5x. Those cancel out. We also have a 2 and a negative 2. It really helps to circle them rather than to cross them out so you can see your work. But as you can see, a lot of stuff cancels out. Now we keep going. Now let's write down what's left. We have the limit as h approaches 0. Left up in the numerator is just 5h over h. Now, we have a limit problem here. We still cannot do direct substitution. That's why we're doing all this work, so we can get to a point where we can just plug in 0 everywhere we see h. But we can't plug in 0 yet because we're dividing by 0. I do have 0 over 0. That tells me there's a limit. So now I want to simplify. We know that these h's are going to cancel out. Anything over itself is 1. So now I have the limit as h approaches 0 of 5. Now I can do the direct substitution. There's nowhere to plug in 0 because there's no h anymore, but I can use my limit property. The limit of a constant is that same constant. So the limit as h approaches 0 of 5, of course, is equal to 5. All right, the limit of a constant is that same constant. So my derivative function, f prime of x, is a constant function, 5. All right? Now let's talk about it. It kind of makes sense. My original function up here, that is a line. We know all along a line, a slope is constant because the steepness of a line never changes. So doesn't it make sense that the derivative of this linear function is a constant function? There you go. All right, now we can find the slope of the tangent line at any point. Right here, we can find the slope at x is equal to 2. We use our derivative function. We find f prime of 2. Well, we take our derivative, 5, and if we plug in 2, it's still 5 because it's constant. No matter where we take the derivative will always be 5 because our derivative function is constant. Okay, let's tackle example number 2. Let's set up the derivative definition. The limit as h approaches 0. The first part of my numerator is I rewrite the function. I like to put in a blank set of parentheses everywhere I see x, and instead of putting in x, I put in x plus h. X plus h. All right, if you like to label it, that is the first part of my numerator. That is my f of x plus h. All right, now I do the second part of my numerator. In parentheses, I put the function as is, x squared plus x. All right, and that is the second part of my numerator. So if you break it down into 2 parts, it's not too bad. You rewrite the function. Everywhere you see x, you put in x plus h, and you write the function. The denominator, simply h. All right, the second step is expanding algebra. So the limit as h approaches 0. If I square x plus h, remember I get x squared plus 2hx plus h squared. And now I just move from left to right. I still have plus x plus h, and now I distribute this negative, negative x squared and negative x. So that second step is expanding all over h. Now, if you do it correctly, a lot should cancel out. We have x squared and negative x squared. All right, then we also have a positive x and a negative x. So that's everything that I see that cancels. Now we go to the next step. The limit as h approaches 0. What's left? We still have 2hx, and we still have h squared, and we still have an h. We have 3 things left, all over h. Now, I still cannot do direct substitution, but what I can do is I can divide each of these 3 terms in my numerator by my denominator. So that looks like this. We have the limit as h approaches 0. Oops, typo. Okay, if I divide the first term by h, 2hx divided by h leaves me with just 2x. The h's cancel. If I divide the second term, h squared by h, I'm left with 1h. And finally, if I divide my third term by h over h, anything over itself is 1. h over h is 1. All right, now I can do direct substitution. I can plug in 0 everywhere I see h. So I have 2x plus 0 plus 1. Essentially, every term with an h in it goes away. So my derivative function is 2x plus 1. All right? Look at this. My original function was an x squared. My derivative function is an x to the first. And that's a key relationship. Every time you take a derivative, the degree goes down by 1. So the derivative of a quadratic x squared will be a line, x to the first. Okay, let's find the slope at 2. So we want f prime of 2. So we plug 2 into the derivative. 2 times 2 plus 1, my derivative is 5. And the derivative at negative 1, the slope of the tangent line at negative 1, we want f prime of negative 1. That gives me 2 times negative 1 plus 1. I'm going to squeeze it in here. That gives me negative 1. All right, so my derivative function is 2x plus 1. The derivative at 2 is 5. The derivative at negative 1 is negative 1. Okay, example number 3. One last time. Set up the definition. The limit as h approaches 0. Rewrite the function. X squared plus 3x plus 1. I like to rewrite the function and put in a blank set of parentheses everywhere x is. Now I plug in x plus h, and now I have to plug it in twice because there's 2 x's in my original function. So this whole thing right here is my f of x plus h. That's the first half of my numerator. The second half of my numerator, I just plug in the function as is. X squared plus 3x plus 1. And if we label that, that is my f of x. All right? Okay, second step, now I just go to work and I expand. So I still have the limit as h approaches 0. If I square x plus h, remember I get x squared plus 2hx plus h squared. Now I have to distribute the 3x plus 3h. Working to the right, don't forget plus 1. And finally, the last thing to do is distribute this negative. I have negative x squared minus 3x and minus 1. Don't forget to distribute that negative. Okay, the next step, if you do this correctly, a lot should cancel out. Circle them. I've got a positive x squared, I have a negative x squared. I've got a positive 3x, I've got a negative 3x. I've got a positive 1 and a negative 1. Okay, so now I like to write down what's left. I still have a 2hx. I still have an h squared. And I still have a 3h. All over h. Okay, now I still can't do direct substitution, but I can divide all 3 terms in my numerator by h. So I still have the limit as h approaches 0. If I take the first term and divide it by h, the h's cancel and I have 2x. If I take the second term, h squared divided by h, that leaves me with plus h. And finally, if I take the last term, 3h, and divide it by h, the h's cancel, and I'm left with plus 3. Now I can do direct substitution. So I plug in h everywhere, 0 everywhere I see h. So I have 2x plus 0 plus 3. Alrighty? So my derivative function is 2x plus 3. Check it out. The degree went down by 1. I have a quadratic x squared. My derivative is x to the first. So the derivative of x squared plus 3x plus 1 is 2x plus 3. Finally, let's find the derivative at negative 2. So we want the derivative f prime of negative 2. All right, so that gives us 2 times negative 2 plus 3. That gives me a derivative of negative 1. So at negative 2, the derivative, the slope of the tangent line is negative 1. All right, and lastly, we want to find the derivative f prime of 3. So we plug 3 into the derivative function. 2 times 3 plus 3. And that gives us 6 plus 3, that gives us 9. All right, there you go, definition of derivative. Thanks, calculus.